Onward! Here we go. Alright, here's the data booklet and all of that stuff we just covered. You're going to find it right in here. R equals V over I. Right? There we go. Power equals V times I equals I squared times R. R equals V squared divided by R. Okay, so it's all right there for you. What is the voltage of a battery that produces a current of 1.5 amps through 3 ohm resistor? Pause it. Try these two problems. Second one. What resistance would produce a current of 5 amps from a 120 volt power source? Ready? Here we go. Maybe. There we go. I equals 1.5. R equals 3. V equals I times R, which is 4.5 volts. For the second one, we have I equals 5 amps. V 120. V equals I times R, rearranged, and we get 24 ohms as our answer. If we were to graph Ohm's law, if we were to graph current versus potential difference, we should get a linear relationship. And that means a linear relationship means our component is ohmic. So if you have an ohmic resistor, then that means you have a linear relationship when these two are graphed. As you increase your potential difference, your current is also going to increase. So your resistance is constant. So if you are looking to decide whether or not a resistor is ohmic, then you have to see what happens as you're changing your potential difference or as you change the current within your circuit. Okay, one reason why the IB book is rearranged in this way, where R equals V over I, is because R is going to remain constant. Okay, many or most electrical resistors don't follow Ohm's law all the time. For example, incandescent light bulbs have much more resistance as they heat up. Nonlinear relationships mean that our component is non-ohmic. A word about light bulbs here. All right, so the way light bulbs work is you have to have current coming in, and it'll come in probably through the side and touch this metal conductor, and then the current is going to come up here, and then it's going to reach this little springy looking thing, the filament. And that filament is made of tungsten because tungsten is super resistive. So the resistivity of it is very high, so high that as the current is pushing through, it's kind of like a frictional situation where a lot of the heat, the electric energy is transferred into heat energy. And just like when you rub your hands and you get that heat, that friction, then the tungsten heats up. This happens so quickly and to such a great extent that the tungsten actually radiates. It emits heat and glows to produce light bulb, to produce a light. So that is the idea of the light bulb. And then the current will come down here and go straight out the bottom and continue on its path. All right, so if we're looking at the IV graph for a filament lamp, resistance increases at higher temperatures. Ohm's law only works if the temperature is constant. IV graph for a thermistor. Resistance decreases at a higher resistance. At a higher temperature. So resistance is going to go down, so our current is allowed to go up exponentially. For an IV graph for a semiconductor diode just has the controls the direction of the flow of the current. Current is negligible in this direction. Meanwhile, current is allowed to flow in this direction. Not linear relationships, not ohmic. Non-ohmic, in fact. All right, so find V and R for the resistors X and Y when the current is 2 amps. Go ahead, pause it, try it for yourself before we go on. And we're back. Boom! There we go. When current is 2 amps, we're going to go to the 2 amp current, and we're going to come over here, and we see that X crosses the 2 amps when the potential difference is 4 volts, and Y crosses 2 amps when the potential difference is 10 volts. So we have 4 volts, 10 volts. Current is 2 amps for each of them, and then we would just use R, V equals IR for each resistor. To combine resistors, when the current has no choice but to follow this path, this is called being in series. If the current does have a choice, can make the decision to either go left or can go right, then we call that circuit parallel circuit. And this can happen for an infinite number of resistors. It can be 10 resistors in series, it can be 5 in parallel, it doesn't matter. So either way, if there is this junction right here where the current has the option to pick one path over the other, then we call that being in parallel. Any of these junctions. All right, here's what I want you to do. I want you to grab some straws, and you're going to slice them up just like this. So pause it, slice them up just like this. We got a whole straw, we got 2/3 of a straw, 1/3 of a straw, 2 short straws, and 3 short straws. All right, here's your activity. With the same full deep breath for each setup, time how quickly you can completely exhale all of your air. So use your phones as a stopwatch, take the whole straw, blow through, see how that compares to 2/3 of a straw, 1/3 of a straw. So the whole straw represents 3 resistors in series. Oh, that's ugly. 2/3 of a straw, 2 resistors in series. 1 resistor is just 1 resistor. 2 short straws are 2 resistors in parallel. Meanwhile, 3 short straws are 3 resistors in parallel. So as you did this, perhaps you saw your time decreasing. And that's because as you got into parallel, you experienced less resistance. When done collecting your data, answer the questions on the next slide. What does this model show about resistors in series? What does this model show about resistors in parallel? Complete the activity, pause it. Answer these questions. There we are. Adding resistors in series increases the overall resistance. Adding resistors in parallel decreases overall resistance.